Now in this time, I will talk about the tight binding model. Chapter 11 is the tight binding model. Then we know there is a periodic potential if the atoms make a periodic potential. It is a one-dimensional potential, and then this potential like this, it is a negative potential. Then the energy in the energy case, there may have the potential. It is a negative potential, but the positive potential can be considered like this. And the negative potential and positive potential, the concept is identical with each other. And anyway, when you consider this potential step in chronic-Penny model, and the chronic-Penny model assumes that energy, it is a potential height, and the potential height is V, but here the energy is below the potential, and here it is assumption of the chronic-Penny model. It means that potential is enough high comparing with the energy. Then we call it is a nearly free electron model. In nearly free electron model, they affect the potential effectively, and the potential and the periodic potential makes the Bragg reflection of the electron wave function that is caused the formation of the energy band gap. But in the more high energy, for example, energy is higher than the potential, and the energy is very high of the kinetic energy. For example, kinetic energy very high comparing with the potential energy. We call it is a free electron model. Free electron representative free electron model is that I will describe later. It is a Drude model. Drude model or a Sommerfeld model. And they do not feel the electronic potential. And the background is smearing out, and because the electronic kinetic energy is very high, they move freely without consideration of the potential step or a potential periodic potential. Therefore, however, if the energy is very low comparing with the potential, then we feel that energy is very low comparing with the potential. Then potential, it means that potential is dominant. And in this case, electron wave function is localized into the atomic orbital. And the model, the tight binding model, deals with the high potential strength and also low kinetic energy. Therefore, the tight binding model is the opposite limit to the nearly free electron model or the free electron model, and it is high potential case. High potential, and also it can be described very well it is a useful model for the insulators, because insulators are electronic wave very well localized in the atomic orbitals. But also in other case, but in metallic case can be applicable in the tight binding model. For example, it is the d orbitals, transition metal d orbitals, or the rarest f orbitals. Then it is well described, and therefore, when we consider that, we briefly introduced that when we use the tight binding model, and there are three assumptions. The first one is that close to each lattice points, the crystal Hamiltonian means that real Hamiltonian in the crystalline lattice, and can be approximated by an atomic Hamiltonian. And the atomic Hamiltonian. And it is very reasonable assumption because the electronic wave is very well localized to the atomic orbitals and each lattice points, and the crystal Hamiltonian is very close to the atomic Hamiltonian. The second assumption is that the bound levels of atomic Hamiltonian are well localized. It means that potential is very high. Potential is so large that the electrons are bound to ionic cores. And the bound levels are very well localized in the atomic orbitals. And the third one is that the wave function is a stationary state over the crystal with here the atomic Hamiltonian can be calculated like this eigenvalue problem, and the wave function because the bound state atomic Hamiltonian crystal Hamiltonian can be approximated to the atomic Hamiltonian, and also wave function is so localized, and there we can solve the eigenvalue problem by the atomic Hamiltonian, and also there should have the wave function should follow the Blocher theorem, exponential I k dot r psi r, and this should follow the Blocher theorem because of the translational symmetry. And it is a basic concept of the tight binding model. And let's consider for the general formalism of the tight binding model. And atomic Hamiltonian psi n equal to epsilon n, psi n should be calculated. But in real crystal Hamiltonian, and the real atomic atomic Hamiltonian problem is not a solid state problem, but it is a quantum mechanical problems. But here, and therefore, the crystal Hamiltonian should be write down is the atomic Hamiltonian plus derivation over the potential. It is small potential corrections. Because potential is very weak and the atomic Hamiltonian is dominant, but this correction to the atomic potential should be very should take into account anyway. And also in this case, psi n r is the periodic potential and levels in periodic potential. Also, there should have the Blocher theorem. Psi and k R should follow that the summation from the reciprocal lattice vector exponential I k dot R and also psi n R minus R. Here it is a linear combination of wave function and R is the Bravais lattice. Therefore, it should follow the Bloch theorem. And it follows the Bloch theorem, and we can prove that it follows the Bloch theorem. And we can prove that like this. And psi n k R plus R, it is the real space vector, and also can be calculated Bravais lattice R prime exponential I k dot R prime and the psi n R plus R minus R prime. Here R plus R plus R, and minus R prime. Then it can be written like this: exponential I k dot R, and also summation with R prime, and exponential I k dot R prime minus R, because this R minus R prime and IR cancel with each other. And also psi n minus R prime minus R. Then exponential I k dot R, and the prime can be neglected, and here let's define that R bar. Then it is exponential I k dot R bar, and R bar is R prime minus R, and the psi n R minus R bar. Therefore, it is the same with the exponential I k dot R, and also it is psi n k R. It is the same with psi n k R. Therefore, it follows the Bloch theorem like this, and it proved like this. Here, then we should think about that. We should prove that this atomic Hamiltonian H psi epsilon psi. Then here the Hamiltonian is the atomic Hamiltonian plus delta V, and also it is epsilon psi n psi. Therefore, we should prove this equation. But in this case, because we think about that initial assumptions, and we think about that the atomic wave function, modify the atomic wave function, not the real wave function in crystal Hamiltonian. Let's consider wave function, and let's assume that phi r is that modified wave function of atomic Hamiltonian, atomic wave function psi n r, and also it is the psi n r is the atomic wave function, and phi n is the modified wave function, and here the general form of wave function for the crystal Hamiltonian and we can write down phi r is that summation for with respect to Bravais lattice, and exponential I k dot r, and modified wave function R minus R. It should follow the Bloch theorem. And also phi r means that here phi r is the linear combination of the atomic wave function, then we can understand that actual phi n is the atomic wave function. It is atomic wave function, and the summation with Bn. Bn is coefficient. It is a linear combination of the each atomic wave function. Also, then this it is a modified wave function. Modified wave function of the crystal Hamiltonian, and actually then we can understand that there is a periodic potential. In periodic potential there is the real wave function. We call it is psi n. It is the atomic wave function. But in crystal Hamiltonian, then it should have the linear combination of the each atomic wave function. It is that phi r, and also this phi r should follow the Bloch theorem. That's why we expressed like this, and it follows the Bloch theorem generally, and therefore, we should think about that this wave function, and here you can understand the physical meaning or the physical idea on this wave function. Then we should prove that the eigenvalue problem, and H psi r is that atomic Hamiltonian plus potential psi r. Then it is the energy eigenvalue and psi r. And in order to have the to solve this expectation, in order to get the expectation value, and we multiply the complex conjugate and integral of the entire space. And here, then let's consider for the atomic Hamiltonian case, especially in this case, and atomic Hamiltonian and also psi r. Then in order to have the expectation value and the psi theta and also dr integration, then in this case, and they can be write down real, because atomic Hamiltonian is a real value, and because it is a physically real or a mathematically real value, and the psi, it is a Hermitian conjugate anyway, and star, let's say that it is m, and psi r. Psi m means that it is the atomic wave function, and here, because atomic wave function is so well defined, and it is here em and also integral psi m star r and psi r dr. It is the atomic wave expectation value of the atomic wave function, and also therefore in the total case, and in total, and the psi m star r h psi r is the expectation value for the whole crystal Hamiltonian. Then, because we know that it is atomic Hamiltonian component is that em psi mr and psi r dr. And also we should consider for the potential energy term psi m star delta v r and psi r dr. And also it equal to energy and integration psi m star r psi r dr. Then it is the expectation value for the whole system. Then, because let's summarize this one, and in this case the epsilon k minus em integral psi m here it is a star r psi r dr equal to psi m star delta vr psi r dr. Here, then we should calculate this term, and also here psi m star r psi r dr is that summation. Because psi r is defined in the above like this, and let's memorize this equation, and then it is that summation with Bravais lattice and psi m star r and exponential I k dot r, and also then in the phi means that the linear combination of the atomic wave function, and therefore it is summation n bn psi n r minus r dr. It is the from the definition of the psi r. It is a real crystal wave function. Then, because it is a summation with respect to the Bravais lattice, and let's consider that on-site Bravais lattice and the except the on-site. And for this case, for the r equal to 0, then we do not consider for the r, and also only consider for n, and psi m star, and also bn psi n r minus r dr. It is that on-site r equal to 0 case, we call it is on-site. But the other case is that summation with n and summation with r, but it is not equal to 0. It is not on-site, and also psi m star r bn psi n r minus r exponential I k dot r dr. Therefore, then let's make this here. Let's insert these equations. Then the epsilon k minus em, because in this case we call it is here, because psi m and psi n r minus r and r, because of the periodic lattice, r minus r and r identical point. Therefore, it is the Kronecker delta mn. Therefore, only the components m equal to n case survives. Otherwise, it's 0. Therefore, it is a bm. It becomes the bm. Then, in the this term still be considered, and minus epsilon k minus em summation n summation r equal to r is not 0, and the summation psi m star r psi n r minus r and exponential I k dot r dr, here bn. Yeah, and also the last term, this last term also can be treated like this. Then the first term is the on-site. The on-site case. On-site is that r equal to 0 case, and summation with n integral psi m star r, and also here delta vr psi n r bn dr. It is on site. Anyway, I'm sorry. It is not r minus r, but r. And therefore, it is exactly Crank delta mn. And also it is on site and the other side. Summation n, summation r is not equal to 0, and the integration psi m star r delta vr and psi n r minus r bn exponential I k dot r dr. Anyway, it's a little bit complicated, but the basic idea is that from this, the atomic Hamiltonian, the crystal Hamiltonian, we apply the expectation value calculation, and also by definition of this wave function definition, then we apply this one and the one side and the other side. Yeah, then we can obtain these equations, and also then let's assume that there are several assumptions. And the several assumption, the first assumption is that psi m star r and psi n r minus r dr is very small, because that psi mr is the r side, psi n r minus r is the other side. It is nearest neighbor, and the nearest neighbor orbital wave function overlap is very small. It is first assumption, and the second assumption also similar. In psi m r delta v r, and also psi n r minus r dr also very small. It is similar with the first assumption. And also in the actually in the other case also, in the final term, when you assume that the final term also very small, then because atomic wave function is very small at distance large enough from the periodic potential, therefore the old term, this term and this term is very small. Therefore, the energy eigenvalue and the energy eigenvalue is close to the atomic energy. Then it is a trivial case, but in real calculation, we should take into account all the terms, and also here the summation for n is the summation for the quantum numbers. For example, S level, P level, and the D level, and when there are several quantum levels, and R means that Bravais lattice vector, and therefore in the later, and let's calculate the one example for simple cases.